you'll visually see using your calculator how that rolls out. Okay, so let's start with cosine x equals negative root 3 over 2. So last week we learned two methods for solving graphically, the intersection method and the x-intercept method. Let's just use the intersection method. Okay, so you just need to graph. They're giving us a scale in degrees, so our mode should be degrees. And our window settings should also be in degrees. So I'm just going to go -1 to 360 with a scale of, we take a look, 180 divided by 6 spaces, that gives us a scale of 30 degrees. Y min, I'll just go -2, Y max 2, and I'll scale up by, 1 should be fine. Okay, so make sure your window settings are something along the lines of those. And then in your Y1, is it okay if I move forward?
Yeah.
Okay, our Y1 will be cosine x. And our Y2 will be negative root 3 over 2. We can graph it. So this is the base graph of cosine showing up, and that's the line of negative root 3 over 2. So just by looking at it, how many solutions do we have between our domain 0 and 360 degrees? What is a solution? Nope. What method are we using? We have two graphs, so we need to look for intersection points. And we have 1, 2. So let's trace these solutions. Second trace, number 5 for intersect. 1, 2, 3. So one solution is 150. Okay, and then the next solution, second trace, number 5 for intersect. Will be 210. My graph's not totally accurate, but we have solutions at 150 degrees, 210 degrees. So we can say that x is equal to 150 degrees and 210 degrees. Now we're going to take a look at the second graph. So is everyone good to move forward? So instead of cosine x, we're going to go cosine 2x. And then graph it, and let's just count how many solutions we have now. Okay, how many intersection points? 4. So it doubled. The graph is compressed by 1/2, so it's going to occur twice as many times. Okay, so we have a solution here, 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 and here. So if you guys could just trace those solutions, let's figure out what we get. I think we can do this mathematically to start. Okay, if we had x-intercept or intersection points at 150, and we know the graph is compressed by 1/2, what's that first intersection point going to be? 75. Good. Okay, and then this compressed by 1/2 will be 105. And let's just trace those last two solutions. So we're getting 255. And do we get 285 for the last one? Okay, so just make sure you draw that graph in there. Now if we had to compare the number of solutions from the graph where it's cosine 2x and the graph where it's cosine x, we could say that we have twice as many solutions. So cosine 2x has twice as many solutions. And what's happening to the values of x? Okay, for example, first we had 150 and 210. Now our first two are 75 and 105. They're being divided by 2, or half, yeah. And I'll just say divided by the b value. Or you could say it's multiplied by the horizontal stretch factor. And in this case, the b value is 2. So we're dividing each solution by 2. So just reviewing from a few lessons back, if we were to talk about the general solution of cosine x equals negative root 3 over 2, okay, what is the difference, or what is the period for cosine x? You guys remember? What's one period for cosine? 2 pi, good, or 360 degrees, because we're talking in degrees. So how would I find the next solution? For example, this just kept going. Oops, went a little too low. So this just kept going and going and going. How would I find these two solutions? And then these two. And then these two. Or if I went backwards, how would I find these two? You're going to have to add or subtract a rotation, or 360 degrees. So the solutions will be 150 degrees plus 360 degrees times n. And then you take the second solution, 210 degrees, and we need to add another period, 360 degrees times n. And just recall that n has to be an integer. Okay, so that's the general solution. Right, x will equal this. Okay, that's a general solution for figuring out the solutions across a domain, all real numbers, where you're going to negative infinity or positive infinity on the x-axis. Now part 2, the general solution to cosine x consists of 2 sets of answers. These answers, sorry I just have to read the fill in the blank here, differ by how many degrees? Okay, 360 degrees, because the period of cosine x has, or is 360 degrees. Now part 3, what would you guys say the period of this graph is? Okay, so for cosine 2x, what's the period? I heard pi, but we're talking about degrees, so it's 180 degrees. So from here to here, that's 180 degrees. This is one period. Okay, so for filling in the blank for part 3, the solutions will differ by 180 degrees because the period of cosine 2x is 180 degrees. So just looking at cosine 2x again, I'll just move it back over here. If I had to describe my general solution, let's just take a look at our solutions first. So what did these differ by? 30. So 75 and 255, they differ by 180 degrees. That's one full period. And then how about 105 and 285? They differ by 180 degrees. So really, for a general solution, we only need to take these two first solutions, 75 and 105, and our general solution, GS, will be x equals 75 degrees plus the compressed period, 180 degrees, times n. And our second solution, 105 degrees plus the compressed period, 180 degrees times n, where n is an element of integers. Okay, that's the general solution for part 4. So long story short, if you have a stretch factor, you just have to consider that the graph will be compressed or stretched. And if it's compressed, you're going to have the b number times of x-intercepts. And our b in this case was 2. So we're going to have twice as many x-intercepts. So now let's explore tan. So using a graphical approach, we're going to do pretty much the same thing. If you guys can, let's just go in between 0 and 360 degrees, okay? We can convert to radians at the end, but our calculator's already set, so let's just go with that. Okay, so your y1, well, my calculator froze, so I have to start it up anyways. But you guys are already set. So your y1 will be tan 2x. And our y2 will be the square root of 3. Just bear with me while I reset my calculator settings. For tan, you might want to go a little lower and higher. I'll go -5 to 5. It doesn't really matter if you leave it though. And my calculator's in radians, so it's going crazy right now. I need to put it to degree mode. So just let it go wild for a second. So if you ever get a graph that looks something like this, hint, you're in the wrong mode. And I forgot to change that. So degree, enter, and I'll just show you your y equals again, tan 2x, and your second graph will be the square root of 3. Now when I graph it, we should get the beautiful graph of tan. Isn't it beautiful? Gorgeous. Okay, so we just need to find the intersection points. Here, 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 here. So we have second trace, number 5, and you'll see your cursor will just jump from curve to curve. We just want to jump till it gets that first intersection point. So enter, enter, enter. And my first intersection point is at 30 degrees. Okay, you maybe have already figured out what the next one would be, but I'm just going to go through the process. Let's trace the second one. Okay, and the way you maybe would have figured out the second one is by thinking about how the period was adjusted. Think about the stretch factor. 120 degrees. Any guesses what the next one might be?
210.
Yeah. And then the next one. So we have x equals 30. What is it? 120, 210, and 300. So I adjusted my window settings to degree, but if I wanted to put this in radians because my original domain was in radians, we would have pi over 6. Okay, 120, let's just go through it. 120 divided by 180, is that 2/3 pi? Figure out in radians. 120 divided by 180. 2 pi over 3. 210.
7 over 6.
Okay, and 300.
Yeah.
5 pi over 3?
Yeah.
Okay, perfect. Now the reason I like to show it in degrees is because I think it's a little bit easier to think about when we're going into our general solution. Okay, it's not necessarily easier to write, but it's easier to think about. Let's talk about tan x to start. What's the period?
Pi. Or 180.
180 degrees or pi, yep. Okay, so then tan 2x, what would be the period? Okay, it's a horizontal stretch factor of 1/2. So now we have a period of pi over 2. So pi over 2, it's like 90 degrees. What do these differ by? 90, 90, 90. Get to the next one. Add 90, add 90, add 90. So to find my general solution, I just start with my 30 degrees. And I can add or subtract 90 degrees times n. And n can be an integer, positive or negative. Okay, so that's our general solution. Starting at 30 degrees, every 90 degrees we're going to have a solution, or an intersection point. Okay, so the general solution consists of answers which differ by pi over 2 radians because the period of tan 2x is pi over 2. So Booker, I don't know if you remember, but last week we got to an example where you were wondering, could we have solved it algebraically? And at that time you couldn't have because you didn't know how, but now we're going to be learning how to solve multiple angle trig equations in an algebraic approach. Okay, so for example, if we have sine 3x equals square root of 2 over 2, first what we need to figure out is what would be the domain for now 3x. Okay, so if we compare sine x, say, to sine 3x, what's happened to the x's? So sine x in comparison to sine 3x. Multiplied by 3, right? So if we were to discuss our domain, comparing x and now all of a sudden it's 3x, the x was multiplied by 3, so what's going to happen to the domain? It's actually going to multiply by 3, but we're going to divide later. So it's going to go to 6 pi and 0 multiplied by 3. It's just 0. I ran into this question with the other class, and I think it's probably best if we just, let's go through the full exercise and then we can talk about why or why not after. But long story short is, what we're solving for originally is going to be sine x across 3 sets of domains. Okay, so instead of to 2 pi, we're now going to 6 pi. And then we're going to take those solutions all the way to 6 pi, and then we're going to divide those solutions by 1/3, or sorry, 3, or multiplying by 1/3. And that will give us all the solutions within 0 to 2 pi. So first we're stretching the domain, we're figuring out all the solutions from 0 to 6 pi, then we're taking them, dividing them by 3, so it's just within the original domain. Okay, so I think it's best if we just look at the process and then we can talk a little bit more after. Okay, so what we're going to do first is just look at sine, and when sine has a positive ratio, let's use our cast rule to remind us where we would be. Okay, so what quadrants, if we have a positive ratio, will sine be in? 1 and 2. Okay, so we have solutions in quadrants 1 and 2. Then we have to look at the ratio. And thinking about our special triangles, we should automatically know that we'll have 45 degrees. Good. Okay, because root 2 over 2, that's special angle, 45 degrees. Or you could go second sine, don't worry about the 3x, just go second sine root 2 over 2. And you'll get x equals 45 degrees. Okay, or you can say pi over 4 if we're talking about radians. Okay, so in quadrant 1, if we use a reference angle of 45 degrees, our solution is 45 degrees. Sorry, 45 degrees or pi over 4 is our reference angle. So we can say that in quadrants 1, 3x will equal pi over 4, or in quadrant 2, we're going to have 180 minus 45, so that's 135. Or we could go 1 pi minus 1/4 of a pi is 3/4 of a pi. So that's just for the domain 0 to 2 pi. We have to do another cycle to 4 pi, and then another cycle to 6 pi. Okay, so to figure out our next solutions, we're going to have to add 2 pi to our previous solutions. Okay, so if these are our base solutions, pi over 4 and 3/4 of a pi, the next set of solutions from 2 pi to 4 pi will be 2 pi plus 1/4 of a pi. It's almost like finding coterminal angles. We're just adding the period each time. Okay, and then the other one within this range will be 3/4 of a pi plus 1 full rotation, or 1 full period, 2 pi. Then if we go even further to 4, in between 4 pi and 6 pi, we're going to add 2 rotations. Sorry. So it's going to be 4 pi plus pi over 4, and 4 pi plus 3 pi over 4. So instead of 2 solutions, we now have 6 solutions, because sine is compressed by 1/3, right? So if it's compressed by 3, that means we're going to have 3 times as many solutions. So we have 6 solutions now. So let's just summarize what our solutions are. We have pi over 4. We have 3 pi over 4. Okay, 2 pi plus pi over 4. That's going to be 8 pi plus 1 more pi is 9 pi over 4. 4 times 2 is 8 plus 3 is 11 pi over 4. 4 times 4 is 16. 16 plus 1 is 17 pi over 4. Excuse me. And lastly, 4 times 4 is 16. Plus 3 is 19 pi over 4. So those are the solutions for 3x. But now we want to compress this. We want to find the solutions between 0 and 2 pi just for x. So instead of 3x, we need to take all of our solutions. If we just want x by itself, we got to divide by 3. And we also need to divide every single one of our solutions by 3. So working through it together, we have pi over 12. Okay, 1/4 divided by 3 is 1 over 12. Okay, the 3's will cancel out, we get pi over 4. 9 divided by 12, that can reduce to 3 pi over 4. Okay, then we get 11 pi over 12, 17 pi over 12, and 19 pi over 12. You're just dividing the denominator by 3. Or multiplying, sorry, the denominator by 3. So just take a moment, and I want you guys to figure out, are there any differences for a general solution? For example, between pi over 12 and pi over 4, would it be the same difference as pi over 4 and 3 pi over 4? Yeah. So you can, is it? Don't think so. But there would be a common difference between these two, and a common difference between these two, and a common difference between these two, and a common difference between these two. Sorry if I'm drawing little Christmas designs now. Let me just erase this. Okay, let's talk about pi over 4. Okay, what would be the difference between pi over 4 and 11 pi over 12? Okay, if I want a common denominator, I multiply by 3. and I get 8 pi over 12. Okay, let's see if I do the same thing here and here. 3 pi over 4, subtract pi over 12. Okay, I need a common denominator of 3, so I'm going to multiply by 3, and I get 12. Multiply this by 3, I get 9. 9 minus 1 is 8 pi over 12. Same differences, right? So for our general solution, we should have our first two values, pi over 12 and pi over 4, and we're just adding the new period, which happens to be 8 pi over 12. So I'm going to just simple it down a little bit, because you're probably a little lost with these pi's, aren't you? Okay, so sine x normally has a period of 2 pi, right? Okay, I might have to backtrack for a second. And then sine 3x would have a period of 2 pi divided by 3. So these are supposed to be the periods. Let me just check something. Maybe I wrote down the solution incorrect. They're supposed to differ by 2 pi over 3. It does? Did I do that? Oh, I didn't reduce it. No wonder. Okay, thank you. So we take 4 out, 2 pi. Okay, good. It's like something seems off here. Good. So we're seeing a difference of 2 pi over 3, and that's what our period of our new graph is. Thanks for the help. Okay, so the general solution will be using the new period. So general solution, we take our first two values of x, and we just have to add our period. Okay, so pi over 12 plus 2 pi over 3 times n. And pi over 4 plus 2 pi over 3 times n, where n is an element of integers.
Why don't you use the solutions we found for 3x?
Say that again, sorry?
Why don't you use the solutions that we found for 3x?
Okay, good question. If we go back to the domain, it says where x is between 0 and 2 pi. So it wants the solutions for x. Okay, if they wanted the solutions for 3x, you would have to use this here. You would see this domain. So 3x goes between 6 pi and 0. Okay, so really good question.
And then we just use pi over 4 plus 2 pi over 3 pi over
So
4.
in the case if it described this domain, yes, so your general solution would be pi over 4 plus 2 pi n. And 3 pi over 4 plus 2 pi n. Okay? Just so you're aware, you're probably not going to see this case where they're asking for solutions within this domain where it's 3x. You'll pretty much, I'm going to just throw myself out there, but pretty much close to 100% you're going to see where they want you to solve for x. Okay? So you will always have to take your solutions, then divide by that b value. Okay? But yeah, that's something to be aware of. Be careful with your domain. So we could verify with the calculator. We would just see that we have 6 solutions within a domain of 0 to 2 pi when we graph this. And as a general solution, they would differ by 2 pi over 3. Okay? Or if we thought about 360 divided by 3, they would differ by 120 degrees. The general solution consists of 2 sets of answers. So this is our first set, second set. Okay, and they differ by 2 pi over 3 radians because the period is 2 pi over 3. Okay, so you always look at what's your new period. That's going to help you find your general solution. So now that we've gone through an example, we're just going to do another one together. And this time the steps are listed out for you. Okay, so step 1, you have to find the domain for the multiple angle. So if you have a 3x, then you need to multiply the domain by 3. Okay, if you have a 2x, you multiply the domain by 2. Okay, step 2, solve for the multiple angle between 0 and 2 pi using the cast rule and the reference angle. And then step 3, you're going to add the period of the trigonometric graph of the multiple angle to each of the answers in step 2 until you cover the domain that we figured out in step 1. Okay, so a little bit easier when we just go through it. Number 1, let's figure out our domain. Okay, so if we're starting with x is between 0 and 2 pi, the new domain will be for sine 2x. So if x is multiplied by 2, then all the values in the domain are multiplied by 2. So we have solutions between 0 and 4 pi. Step 2, sine 2x is equal to negative 1/2. So using the cast rule, we've got to figure out what will our solutions be given the reference angle. So sine is negative, that means we have solutions in quadrants 3 and 4. And your reference angle, you can just go x is equal to second sine 1/2, or we can use our special triangles. And we get 30 degrees. Okay, so we're going to take that reference angle 30 degrees and let's apply it in quadrant 3. So we'd go 180 plus 30, we get 210. I'm sorry, let's just state that's 2x equals. So we get 210 degrees. In quadrant 4, it's going to be 360 minus 30, so we get 330 degrees. But 0 to 4 pi is actually like 0 to 720 degrees. So we have to keep going. Okay, the period of sine is 360. So we need to go now 210 plus 360. And we take the 330 and we add 360. Let's just see what we get. So 210 degrees, 330 degrees, 210 plus 360, 570. And 330 plus 360 would be 690 degrees. So those are solutions for 2x between a domain of 0 to 4 pi. But they didn't want our solution between 0 and 4 pi. They wanted a solution for x between 0 and 2 pi. So we're going to take all these solutions and we need to solve for just x. So divide everything by 2. So we get 105, 165. What's the next one? 285. And 345. Okay, so those are the solutions for x within the domain 0 to 360. But let's keep in mind our domain was in radians, so maybe we should make sure we answer in radians, okay? So from 0 to 2 pi, let's just convert 105. I don't have my calculator on me, so you guys just have to help me. 105 divided by 180. As a fraction, what do we get? 7 pi over 12. Okay, and then 165 divided by 180. Thank you. 11 pi over 12. And 285 divided by 180. 19?
Yeah.
Pi over 12. And the last one, 345 divided by 180. 23 over 12. Okay, so these are now our solutions between 0 and 2 pi. So just be really aware of what your domain is asking. If it's in radians, give your answer in radians. If it's in degrees, give your answers in degrees. For me, I always find it easier to work in degrees and I convert later. So let's think about our general solution now. Hey, do you guys see any relationship between, say, 105 and 165? That would be consistent between 165 and 285? No, but there might be something consistent between 105 and 285, as well as 165 and 345. And that difference is they differ by 180 degrees. Let's just talk again about this 2. Okay, it's a compression by 1/2. So if the period was 360, now it's 180. So these differ by 180 degrees. Okay, or we could say they differ by pi. So now we can just take our first 2 solutions and write them into a general solution. Okay, so we can say that x equals 7 pi over 12 plus pi times n, and 11 pi over 12 plus pi times n. And don't forget, n is an element of integers. So the sets of answers, they differ by pi radians because the new period is pi radians. So before we get to an application, do you guys want to take a bit of time and practice, or do you just want to roll through? Alright, we have an application with the Ferris wheel. Might get you to practice after so I can see how you go. Yeah. Okay, the distance above ground of a student on a circular Ferris wheel is given by the following equation. H is the distance above the ground in meters, T is the time in seconds, when the student is at its lowest point of the ride for the first time. So we have to determine, for part 1, determine the time it takes the Ferris wheel to make 1 complete rotation. Okay, another word for 1 complete rotation is figure out what is the period. So to figure that out, period is given by, in this case it's a cosine graph, so 2 pi divided by the b value. So we have 2 pi divided by pi over 12. Okay, this is our b. So the pi's will cancel out. We get 2 times 12, 24 seconds. So it takes 24 seconds for 1 complete rotation on this Ferris wheel. Seems pretty quick. Okay, now algebraically we have to determine the times during the first minute, so the first 60 seconds of the ride when the student is 7 meters above the ground. So if you were to ask to do this graphically, you would have y1 is your graph, y2 is 7, and you would find the intersection point where they first intersect. And then, actually you could just look at all the times up to 60 seconds. Okay, but we're doing this algebraically, so we have to set the equation equal. Okay, we'll have 7 is my height for h, and that will equal negative 4 cosine pi over 12 t plus 5. So first step, we want to isolate that cosine trig ratio. Okay, so let's subtract 5 on both sides. Then we get positive 2 equals negative 4 cosine pi over 12 t. Then we can divide both sides by negative 4. And we get negative 1/2 equals cosine pi over 12 times t. Okay, this is going to be the equation that we're working with. So if they had given us a domain, we could multiply by that b value in front of the t. But in this case, they're telling us that we just have to figure out solutions within the first 60 seconds. So I'm just going to show you guys a little shortcut instead. Let's jump to step number 2. Okay, so ignore the domain for one moment, we'll go back to that. Step number 2. So if we have negative 1/2 equals cosine pi over 12 times t, okay, cosine is negative in which quadrants? 2 and 3. Good. Okay, now we need to find our reference angle. So t will equal second cosine 1/2. Or we can use special triangles where x is the half. You guys should get 60 degrees. So our reference angle is 60 degrees. And if we put that in terms of radians, you could say pi over 3. Okay, that's our reference angle. So now let's apply that solution in quadrants 2 and 3. So pi over 12t will equal, okay, we have 180 minus 60 is 120 degrees. And 180 plus 60 puts me at 240 degrees. And we're going to be working in radians, so let's just convert those right now. Pi over 12t equals, is it 2 pi over 3? 120?
Yeah.
2 pi over 3. Okay, 240?
4 pi over 3.
4 pi over 3. Okay, we need to figure out the solutions of t, not pi over 12t. So what am I going to do with this pi over 12? Yeah, you can just divide it. Or you can multiply by 12 and divide by pi. I'll just divide like this. Okay, just to show you that we're dividing each solution by pi over 12. So when t is isolated, let's go through this. Our pi's cancel out. I get 12 times 2 is 24, divided by 3 is 8. Pi's cancel out. 4 times 12 is 48, divided by 3, 16. Okay, and if you're unsure of how to do that quickly, just go 2/3 divided by 1/12, and you'll get 8. 4/3 divided by 1/12, you'll get 16. And if you're unsure if the pi's are going to cancel out, you can put your pi's in your calculation too. Alright, so at 8 seconds and 16 seconds, we're 7 meters above the ground. Has that looked at the full domain of a minute? No, so we've just got to take our period now and just see if we're within a minute. So I'm just going to write out the solutions up here so I have a bit more room. So we found 8, 16. To get my next solution, I would go 8 plus the period. The period was 24 seconds for one complete rotation, so 8 plus 24. And then I would go 16 plus 24. And then let's just go to the next set. It would be 8 plus 2 times 24. And 16 plus 2 times 24. So summarizing our solutions, we get t is equal to 8, 16, 32, what do we get here? 40, 56. Hey, do you think I'm going to go over 60 here? Yeah. So that one's past domain of 60 seconds. Okay, so we rule that one out. So these are our solutions. Okay, where we're talking about seconds here. So at 8, 16, 32, 40, and 56 seconds, that's when we have a height of 7 meters.